Hello everyone and welcome back to another video. In this video we're going to move on to section 3.6, which is all about numerical integration. Numerical integration is used to approximate definite integrals. So we already saw some numerical integration techniques, right, when we saw the Riemann sums from chapter 1, right, where we used rectangles, an infinite amount of rectangles, to approximate the area under the curve. So we were using Riemann sums to approximate definite integrals. And the reason why numerical integration techniques are important is because you can't always find the antiderivative of a function. So if we can't find the antiderivative, then we won't be able to find the value of the definite integral, right? Unless we can approximate it using numerical integration. So as we saw, there's a bunch of different integration techniques, right? Using integration techniques, but they work only for specific kinds of functions, and unfortunately there isn't enough integration techniques developed to this day to evaluate every single integral and get an antiderivative. However, because we know the definite integral could be approximated and is equal to the area under the curve, we can continue to use those techniques from chapter 1. So in this section 3.6, we'll learn the trapezoid rule, and we'll also learn Simpson's rule. And we'll also learn how to evaluate or calculate the absolute error, which will be the difference between the approximation and the actual definite integral. But in this video, I will focus solely on introducing the trapezoid rule. So what is the trapezoid rule? Its name is actually pretty intuitive. So instead of using rectangles, right, we're going to use trapezoids to approximate definite integrals. And so I'm going to show you exactly how the trapezoid rule works. So let's take, right, before we go there, right, let's just recall what is a trapezoid, right? So a trapezoid looks something like this or something like this. And the area of a trapezoid is given by the two side lengths divided by 2 times the height of the trapezoid. Right, so that would be A and B, this would be A and B, and this would be our height here, which would be the same height on this side here. So in general, that's the area of a trapezoid. So now let's look at a function, and let's look at how we use trapezoids to approximate the area under the curve, or better yet, approximate the definite integral. So in this image from the textbook, we see that there are a number of rectangles already here plotted for us, right? And we see that the width of the rectangles, of the trapezoid, is all the same unit length, right? So remember that we called the width of each rectangle, which in this case will be trapezoid, the width of each trapezoid is the change in x. The width of each trapezoid, or I should say the height, technically, if we're looking at them sideways here, right? And so then if we try to calculate, let's call this first trapezoid A1. If we try to calculate the area A1, right, we know that the height is change in x, and then we need to find, right, this side, right, which if you notice is just going to be whatever the value of the function is at x0, and we also need to find this height here, which is whatever the value of the function is at x1, right? So this is f of xo plus f of x1 all divided by 2. And then if I look at a2, right, I still am, they share a side, right? So when I go to do a2, right, we have the same height, and then we have f of x1, and now we have at x2, we need to find what the height is there, right, which is the value of the curve there, right, because this curve here is f of x, remember. So this is f of x2. And we continue doing this, right? So if we call this a3, we see that a3 is change in x, and the two side lengths it uses is f of x2 and f of x3. And that's all divided by 2. And last but not least, a4 again has the same sub-interval width, and then right, the two sides it uses is x3, whatever the height is at x3, and whatever the height is at x4. So then the total area under this curve, if we call the total area just capital A, that's going to be the sum of all of the areas of these trapezoid, right? And that's an approximation for the integral of f of x dx from A to B, right? Where B is x4 and A is x0. Right, so one thing that I want you to notice, because they say that the trapezoid rule is an average, so note the trapezoid rule is an average of the left hand and right hand sums, right? When we use the integrals, the left and the right hand integrals. And why is that so? Well, if you notice, right, all of these inner heights here, oops, what happened? Are used twice, right, except for the very first and the very last one. So when we go to write the trapezoid rule in the formal statement, we're going to see this at play here, right? So what the trapezoid rule says is that we assume that f of x is continuous over AB, which remember we need that for it to be integrable, and let n be a positive integer, right? So we need to have a whole positive number for the number of rectangles that we have. And the change in x is still the same. We defined it before as b minus a over the number of trapezoids in this case. And then we're going to let a comma b be divided into n sub intervals, each of length change in x with endpoints at p equal, right, we start at x0, x1, x2, so on, all the way until the very last one. And then tn, right, so we use the notation capital T subscript n as the notation for the trapezoid rule with n trapezoids, is 1/2. Right, so right now what do we have right now, right? What we saw is that it's equal to the sum of all of these, right, in the case of 4 trapezoids, right? So if I was to add these all up, then I would have change in x times f of x0 plus f of x1 all over 2 plus change in x, I'm gonna just do dot 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 all the way until we add on the last one. Why did I put the 4? I must have was thinking about this 4 and accidentally wrote it there. Right, and so if you notice, they all have a change in x and a 1/2 in common, so we can pull that out front, and then we'll have a 1/2 change in x, and then what's left, right, is the sum of all of the inner heights. However, notice that all but the first and the last one get added in twice. So we have the first one with no coefficient, and then all of the ones in between, right, until you get to the one before the very last one. Oops, I'm gonna need more space. Right, the n-1th one has a 2 in front, but the very last one, the nth one, does not. Right, and that's simply because of how the area of each trapezoid is calculated, and when we sum them all together and factor out change in x over 2. So if you notice, this is just a weighted average of the left hand and the right hand sums, because remember, in the left hand sum, right, the last endpoint was not included, right? Like if this was how we split up, if we split up our interval into these sub-intervals with these endpoints, right, on the left one, we don't end up including this one, right, because the last interval is x-1 to xn, and we use this one for our height in the left endpoint rule, versus on the right endpoint rule, we use this one, right? So on the right endpoint one, for the first one from x0 to x1, right, we use x1, so we never actually use x0. So when we add up ln and rn, the first and the last one, right, the first one only gets used for ln, and the last one only gets used for rn, but everything in between gets used for both of them. So that's why we see those 2's there as well. So it all works out that this is a weighted average of just the average of ln and rn, right? So that's all the kinks behind the trapezoid rule. Okay, and so then, right, we know that if we were to use an infinite amount of trapezoids, right, that would be a perfect approximation of the definite integral. So let's do an example using the trapezoid rule. So use the trapezoid rule to estimate the integral from 0 to 1 of x squared dx using 4 sub-intervals. Right, so we know from the statement that n is the number of sub-intervals, so n is equal to 4, right? Our a is equal to 0, our b is equal to 1, and then our change in x, which we know is b minus a over n, then becomes 1 minus 0 over 4. So each of our subintervals have length 1/4. So our subintervals, right, they start at 0, right? They have to be 1/4 wide, right? So I go from 1/4 to 2/4, which is 1/2, and then 2/4 to, right, which is still 1/2, to 3/4, and then from 3/4 to 1. Right, so I'm gonna use this formulation, right? Like if I had ln and rn for this example, then that would be much easier to just plug them into here, but I don't. So if you don't have them, then the first formulation is easier, because if not, you're gonna have to do L4 and R4 separately, right? So I'm gonna take that formula, but I'm gonna do T4 instead of Tn, right? So notice this is my x0, this is my x1, my x1, my x2, my x2 again, my x3, my x3 again, and this is my x4. Okay, so when I set up T4, it's going to be 1/2 change in x, right? And in this case, we only have f of xo plus 2 of f of x1 plus 2 of f of x2, f of x2 plus 2 times f of x3 plus 2, and then we have just f of x4, right, the very last one. So then I plug everything in. Change in x I had was 1/4, and then f of xo, that's f of 0, plus 2, x1 was 1/4, plus 2, f of x2 was 1/2, and 2 times f of x3, which x3 was 3/4, and then x4 was just 1. And then our function, remember, is x squared, so I have to plug all of those x values. Right, this 1/2 times 1/4, I could simplify that as 1/8, and then I have 0 squared plus 2 times 1/4 squared. So remember that f of x in this example is x squared, so we're squaring all of the x values we plugged in to x squared. Okay, so then, right, what do we get? We have 1/8, and then 0 squared is just 0. 1/4 squared is 1/16 times 2 is 2/16, right? Which, so let me just write it separately for now, just to show exactly what I'm doing. So 1/2 squared is just 1/4. Right, and then 3/4 squared, that's 9/16, right, and then 1 squared is just 1. So then we end up with, right, if we want to sum these all together, we're going to need to have a common denominator, so let's just use 16 as our common denominator. So 2 times 1/4, that's 2/4, and then multiply top and bottom by 4, that's going to give us 8/16, and then 18/16, and then 16/16, right? So then 2 plus 8 is 10, plus 18 is 28, plus 16 is 44. So this is 1/8 times 44/16, right? And so then we know that we can divide 44 and 16 by 4, so this really simplifies down. So 1/8 times 11/4, which is 11/32, right? We just multiply straight across, which is approximately 0.34. And that's our approximation for the integral from 0 to 1 of x squared dx. Thank you.